Today we're going to look at exact equations. So the reason I put this in the course is because not only does it give you another way to solve certain differential equations, exact equations, but it gives you some practice of dealing with partial derivatives and calculating them and integrating equations with respect to one letter. Okay, because in later weeks, in the second half of the course, we will go on to look at partial differential equations at least a little bit. Okay, and so I think it's good practice for you to deal with this early on. All right, so let's jump into it. First of all, what is an exact equation? It's an equation that can be written in a certain form, such as what we see in equation 14. Okay, where we have partial derivatives of f with respect to x and f with respect to y in the form of the differential equation. But the question is, how do I know if I have such a form? Okay, so let's start at the beginning now. Suppose we have a function of x and y, and let's suppose it's z. Let's suppose it's differentiable, where x and y are functions of t, another letter t, and that they are differentiable also. The chain rule for partial derivatives is what we have here in equation 13. Okay, and I'm pretty sure we covered this in Math 201. So I've got my notes here on Math 201. We've got some content in week 2 of Math 201 on partial derivatives. Here we've got Clairaut's theorem, which we'll come up to in a moment. But this result, equation 13, is a result for partial derivatives. Okay, so dz on dt is the partial derivative of f with respect to x times the ordinary derivative of x with respect to t plus partial derivative of f with respect to y times the ordinary derivative of y with respect to t. Okay, that's just the chain rule for partial derivatives. Now, if we suppose that f of xy is a constant, so for example, suppose we have something like x squared plus y squared equals 1, the unit circle, right? That would be in this form. Okay, so suppose we have f of xy equals c, where c is a constant, and further suppose that now t is equal to just plain x, then equation 13 simplifies considerably, right? We can replace all of the t's there with x's. Now, what we have on the left is just 0, because if we're looking at z equals f of x, which is a constant, then the derivative of z with respect to x would just be 0, because remember, this is a constant here. Okay, now what's on the right simplifies considerably also, because dx on dt is just dx on dx, which is 1. And then over here we have dy on dx, which is y dash. So we have this equal to 0, and so therefore we can write this in simplified language as f subscript x for the partial derivative of f with respect to x, plus f subscript y for the partial derivative of f with respect to y, times dy on dx, or y dash of x. So this is equal to 0. Okay, now on the other hand, conversely, if we have a differential equation of this form, then we know that there should exist an f such that f of xy is equal to c, which would be the solution of that differential equation. Okay, so suppose now that we have p of xy plus q of xy times y dash equals 0. So that's a differential equation there. So this is exact if there exists a function f such that p of xy is equal to f subscript x and q of xy is equal to f subscript y. Okay, so that equation 15 matches equation 14. And if that's the case, then we know we can get the function f that we're looking for, which solves the differential equation by integrating, essentially. Okay, but more about that soon. So let's have a look at a test for when an equation of the form 15 here is exact. So when is it exact? Okay, so that's proposition 5.1. Suppose P, Q, P subscript Y, and Q subscript X are continuous over a region D. Now that region D is in X and in Y. So you can think of it as, say, a rectangle. The ODE P plus Q times Y dash equals 0 is exact if and only if for all xy in the region D, the partial derivative P subscript Y is equal to the partial derivative Q subscript X. And if you need a proof of this, it's in just about most books on differential equations. It follows from Clairaut's theorem that we learned in Math 201, which is right here. If f and its first and second partial derivatives are defined and continuous, then f subscript xy is equal to f subscript yx, right? Where these are the definitions of those. Those are second derivatives there. Meaning, if it doesn't matter in which order you differentiate f with respect to each letter, then that theorem holds there. Or that's what the theorem says. It holds when the first and second partial derivatives are defined and continuous. Okay, so let's go back here. So it relies on that result, but you can see full proofs in these references here. I've got page numbers as well. All right, so let's have a look at how we actually go about solving an exact equation when it is exact. If we have an exact equation, our next step is to solve for the function f of x and y. This is done by solving two partial differential equations. P equals to f subscript x and q equals f subscript y. Now we do this just by integrating. So we take, say, the top equation here, p equals f subscript x, and we just integrate that. Okay, so where the constant of integration is a function of y rather than c. Right, so I should note that this is a partial integral, even though we have an ordinary d. It's just the convention to use an ordinary d there. Okay, so I think that should say f right here, so that's probably a typo here. That should say f equals the integral of f subscript x with respect to x. So I'll have to go and change that later. And I'll note down my page number 45. Incidentally, I've already fixed the other typos, but I'll update that when I update the second half of the course. Okay, so we integrate that partially. And the constant of integration will be a function of y, because remember, if you take a partial derivative of a function of y with respect to x, that is just equal to 0, because the y's are treated as a constant when differentiating partially with respect to x. So the constant of integration is a function in this case. And so then you have to use the second partial differential equation to find out what that function actually is. Okay, but probably the best way to see this is through examples. So let's have a look here at example 5.1. Show that the following ODE is exact and then solve the initial value problem. Okay, so here we've got an ODE. It looks almost like it would be homogeneous, but you can see it's not because we don't have an x cubed there in the numerator. We have an x squared. So it's not homogeneous. Let's check if it's exact. So first we want to rearrange this equation so that it's in the form of equation 15 here. So we multiply both sides by 3xy squared, and then we take the minus 3x squared minus y cubed over to the left hand side, and we have the form of equation 15, so that we can now set out a p and a q. So let's go ahead and do that. we set p equal to 3x squared plus y cubed, which is what we have here on the bottom left in the position of p, where we see equation 15, and then q will be 3xy squared, which is next to y dash. Okay, so we have that. Now we want to test whether the equation is exact. So we calculate partial derivatives. So we take the partial derivative of p with respect to y. Okay, so that means we're treating x as if it's a constant. So the partial derivative of a constant is 0. So partial derivative of 3x squared with respect to y is 0. And then we move over and differentiate y cubed with respect to y partially, but that's the same as the ordinary derivative of 3y cubed because we only have a y there. So that's just 3y squared. Okay, moving on, differentiating q partially with respect to x. We're taking the derivative of 3xy squared with respect to x. That means we're treating 3 and y squared as constants, so we can pull those out to the front. And then look at the derivative of x with respect to x, which is just 1. So we obtain 3y squared as the derivative of q partially with respect to x. Now you can see straight away that those match, right? So we have p subscript y is equal to q subscript x. So we can say this equation is exact. All right, so moving on, let's go ahead and find f of x and y. So we seek to solve the equation p is equal to f subscript x and q is equal to f subscript y. But let's start by solving the first partial differential equation there. It's a very simple one, of course. Starting with p equals f subscript x, we integrate both sides partially with respect to x, meaning we're integrating 3x squared plus y cubed with respect to x partially, and that just means to assume that y is a constant in this case. Okay, so the integral of 3x squared is x cubed. The integral of y cubed with respect to x, treating this as a constant, is just x times our proposed constant here, y cubed. And then our constant of integration is a function of y because we integrated partially with respect to x. Okay, so that's where the second equation here comes in. The equation q is equal to f subscript y. So what we do here is we take this down the bottom and we differentiate partially with respect to y so that we can then match that with the q that we know is 3xy squared. Okay, so we're just going to take this partial derivative with respect to y in the next line. And so the partial derivative of x cubed with respect to y is 0 because we treat that as a constant. And now moving on to xy cubed with respect to y, well, we treat x as a constant, so we're really differentiating y cubed with respect to y, and we get 3xy squared for that one. Now the derivative of our constant of integration here, but partially with respect to y, that we can just express that as g dash, right? It's the derivative of that function with respect to y. Okay, now we know that this is supposed to be equal to q from our second line of the beginning over here. And so that's what we compare this with. So q was 3xy squared, okay? So then we see 3xy squared is equal to 3xy squared plus g dash of y. Well, that tells us that g dash of y is equal to 0. And so integrating with respect to y just tells us that g must have been a constant. Okay, so now we have our function f, right, that we got down here on the bottom left. F of xy is x cubed plus xy cubed plus a constant. Okay, and so we can just rename that constant to its negative and say that we have the curve x cubed plus xy cubed is equal to a constant. All right, so now we found the general solution to the original ODE. Now what we need is to use our particular initial value to get a particular curve. So let's have a look. what was the initial value here? Y of 1 equals 1. Okay, good. So we'll go back and use that. That says when x is 1, y is 1. So we sub in 1 and 1 for both of those. And we get 1 plus 1 is 2 for C. Okay, so that gives us the particular curve x cubed plus xy cubed is equal to 2. And so now we've solved the initial value problem. All right, let's move on to a second example. But this is a good example because it shows that we do not always have g dash of y equal to 0. All right, so this says solve the initial value problem y dash is equal to minus 2xy over 1 plus x squared plus 3y squared, where y of 0 is equal to 1. So our first step is to rearrange that in the form that we can recognize it as potentially being exact. So we set out p equal to 2xy and q equal to 1 plus x squared plus 3y squared, and we take partial derivatives to check whether this is exact. Okay, we differentiate p with respect to y partially and we get 2x. And now we differentiate q partially with respect to x and we also get 2x. Those match. And so we see that the equation is exact. So now we proceed to find the general solution. So we're seeking a function f such that f subscript x is equal to 2xy and f subscript y is equal to 1 plus x squared plus 3y squared. So what we want to do then is take the first equation and integrate that partially with respect to x. We can straight away see that we'll get x squared y plus a constant, but remember this constant will be a function g of y because that's a partial integral. Okay, so let's have a look at the next page. Integrating, we have x squared y plus g of y. Now differentiating that partially with respect to y gives us x squared plus g dash of y. Okay, and then we compare this result to q, right? Because q was 1 plus x squared plus 3y squared. So comparing that to q, we can see we've got an x squared matching here. But that tells us then, once we solve for g dash is equal to 1 plus 3y squared. Okay, here it's not 0. It is an actual function of y. So we want to integrate to get g of y. But this is a partial, no, this is an ordinary integral. Okay, so we integrate with respect to y, and we have the integral of 1 is y, the integral of 3y squared is y cubed, and then we have a constant of integration. Okay, so now we found g of y, and we can go ahead and replace g of y up here in what f is. So we see then that f is equal to x squared y plus g of y, which was what we just found here. And so we have x squared y plus y cubed is equal to a constant. Now that's the general solution to our ODE. Okay, now we want to use our initial value to solve the initial value problem. When x is 0, y is equal to 1. So we sub in 0 for x, 1 for y, and we just end up with 1 plus 1 is 2. Again, so c is equal to 2, and we have our particular curve. X squared y plus y cubed is equal to 2. All right, now the next topic is what happens if we don't quite have an exact equation, but we can make it exact. Okay, so occasionally an ODE can be made into an exact ODE by multiplying by some function I of x and y, an integrating factor. It's in general not always easy to find that integrating factor, right? So these are difficult types of problems here. Example 5.3, solve y squared minus y plus xy dash is equal to 0. Using the method for exact equations. Okay, now so we set out a p and a q because we've got this in the correct form. We differentiate each of those partially. So p with respect to y gives us 2y minus 1. and the partial derivative of q equal to x is equal to just 1. So the ODE is not exact because these two partial derivatives do not match, right? They're not equal. So without knowing what the integrating factor should be, let's multiply by it. So just symbolically. So I times p plus I times q times y dash is equal to 0. So we want this equation to be exact, though. We want this resulting equation to be exact once we multiply by that integrating factor. So we're seeking an integrating factor I such that the partial derivative of our new p, which is I times y squared minus y, is equal to the partial derivative with respect to x of our new q, ix. Okay, so we take those partial derivatives, but that requires the product rule of differentiation, right? Which says that we put one in front and we take the partial derivative of the other and then we swap them around. Okay, so we have I times 2y minus 1, which is the partial derivative of y squared minus y with respect to y. And then we swap this around, so we have y squared minus y multiplied by the partial derivative of I with respect to y. Okay, and that's supposed to be equal to the partial derivative of ix with respect to x. Now, using the product rule on that, we have x times I subscript x plus I. Okay, so we can now rewrite that as minus x times I subscript x plus brackets y squared minus y, I subscript y plus 2 y minus 1 times I equals 0. And now let's just take a guess that I subscript x is equal to 0. So this simplifies immensely. And we get y I subscript y is equal to minus 2I. Okay, now this one can be solved for I. All right, so we have log of I is equal to minus 2y to the minus 1 with respect to y, or the integral of minus 2y to the minus 1 with respect to y. Okay, this equation here is just separable. So this integral here is easy. We just have log of y to the minus 2, remember. Hang on. Is that right? Yeah, so there's a log rule applied here, which initially makes this look a little tricky. Okay, so you pull the minus 2 out the front of the integral, you integrate y to the power of minus 1, and you get log of y, but then an exponent rule or log rule says you can bring that coefficient inside the log and make it a power. So that's just a log rule applied there. Okay, so so we've got log of I is equal to log of y to the minus 2, and that gives us I equal to y to the minus 2. So that's our integrating factor. So multiplying through gives us now an exact equation. So then we have p equal to 1 minus y to the minus 1 and q equal x y to the minus 2 once we've multiplied through by our integrating factor. So that's now exact, and you can check this. P subscript y is y to the minus 2. Q subscript x is y to the minus 2. Those match, so the result is exact. And now we can proceed to solve our equation using the techniques that we've already learned for exact equations. So we're seeking a function of x and y such that f subscript x is p, which is 1 minus y to the minus 1. F subscript y is q, which is x y to the minus 2. Okay, so again, we can take our first equation, integrate partially with respect to x. So we have the integral of 1 minus y to the minus 1 with respect to x, treating y as a constant. That gives us x minus x times y to the minus 1 plus a function of y. All right, so now our task is to find that function of y using the second equation. Right, we want to take a partial derivative of this final line here with respect to y. Okay, so that derivative gives us 0 for the x part. For the second part, we bring the minus 1 down, becomes a plus with this other minus there, and we have plus x y to the minus 2, and then plus g dash. Okay, so let's have a look. So we have x y to the minus 2 plus g dash of y, and then we compare this with q, which was x y to the minus 2. Okay, so we can see now that g dash must be 0, and then g must have been a constant. So we get the general solution to that non-exact ODE, which is x minus xy to the minus 1 equals c. And rearranging gives us y as a function of x, which is just x over x minus c. But the original equation was separable, so perhaps it would have been easier to use the techniques for separable equations to do that. So let's have a look at doing that via separable techniques and see how hard it would have been. Okay, so I think I'll just pull up a little window here. All right, and where was the equation? We had y squared minus y plus x dy on dx is equal to 0. Okay, so if we do this via what we learned on separable equations, probably actually pretty easy. So let's have a look. So first we want to take this over to the right hand side. So let's just do that. Change the sign of it here. Okay, and next, now let's put the y in front. Next, we put the dx over on the right. Okay, and divide by this one. Divide by the x. So that will give us a 1 over x dx. And then we apply integration signs here. So we've got the integral of 1 over y minus y squared with respect to y is equal to the integral of 1 on x with respect to x. Now that's fairly easy, but it does require using partial fractions with the one on the left, right? Now I can just get the computer to do this without going through the details because we've already done those techniques in previous sessions, right? So this is what we get there, and on the right hand side we clearly get the natural log of x plus our constant of integration. Now on the left we can simplify this using log rules, right? Because we can take this as a difference, and then the log rule says that the difference of the log is the log of the quotient. So I can just put it in like this. Okay, and next we take this as an exponent to base e. So we have e to the power of log is equal to e to the power of this one Okay, so now on the left we just have that quotient of y and 1 minus y. On the right we can just bring out the e to the c and call that a. And then this part here, e to the log x, is just x. So we have this, but we need to do some algebra to finish this off. So what we would do then is multiply both sides by 1 minus y. Okay, now we want to expand the right-hand side. So let's go ahead and expand the right-hand side. Hang on. Okay, now I take all the y's and put them over together on the left and factorize. Right, so we want to factorize the y's out now. And finally divide both sides by 1 plus ax. Okay, and so I expect the solution that we just got should look a lot like this. So let's have a look. Hang on. So we got x over x minus c. All right, now if we let's just divide both sides of this by a, or multiply by 1 on a on top and bottom. So that would eliminate this one, and then we would have a 1 over a out the front here that we could take in. So expanding that denominator, that vanishes this. Okay, so far we've got this, and now we say let 1 on a be equal to minus c. And then we've got the same result using a different technique. All right, so that's all for now. Thanks.